Hello, fans of geometric methods. We have something that I thought would be helpful, but I don't know if it's helpful or hurtful. But let's just do it anyway. So we have a three-dimensional solid in space. The lengths are given, and I made it a triangle just because there's only three lengths that are important in this solid. This distance will be the x distance along this line here. This distance will be the y distance, and this distance, the third one, will be the z. There's a load that hits one corner of it. This load can be moved. This load can be broken down into components, and then you could use essentially two-dimensional statics several times to get the 3D problem solved. But it occurred to me, well, what if we just wanted to solve the 3D problem? Just no two-dimensional statics, just the 3D problem. So for instance, what if I wanted the P3, the vertical equilibrating reaction? One way of doing this is to take moments about the P1, P2 line. But there's kind of a fun thing here that happens that that distance can be found, and we want that distance to be our shortest possible distance. So both of these angles must be 90 degrees for that to be true, right? We could ask the robot for these distances. The distance between the force line and the P1, P2 line. So this is the force line. This is the P1, P2 line. And we could simply ask for the distance between those two. But, you know, that's fairly robotic. What if I manually did this? So what I did was I made a 90-degree angle to the force, found out where that's intersecting this P1, P2, and then I'm just wiggling this. And you could see the insight here, I hope, that this is really a hyperbolic in here. It's a warped surface, and that causes some troubles because when I do force cross radius as a cross product, to get the moment, that moment is not about the 1-2 axis. It's about the axis that is perpendicular to the force line and the radius line. And that line is in this direction. So I think you could see it here. So as I move this, you know, that line changes. So what do I have to do then? So I have to just and obviously I could do this, you know, super cool in this wonderful children's program called GeoGebra. So how do I solve the problem? And that's where it's probably a little ridiculous to do this, but you just take the shooting line of the force. You find that minimum distance. You could ask the robot for help too. Here the robot says 3.765 because I'm wiggling this around. So we just find 3.765. That's as low as we can go and it starts to climb again. So that's kind of a nice insight. But what I really need is this angle in here. The angle to the P1, P2 line. That's what I really need, this direction cosine, which is the shortest angle. And then I could compare the traditional answer, which would just be Fy along the P1, P3 axis times the height, which is Lz, divided by the shortest distance, which happens to be Ly, or 8. That's the traditional statics version. The new version is this one here. So it's the moment about P1, P2. It's that moment divided by Ly. I wrote MON, but it should be MON. So I need that moment, and that moment here is that F2 times this real distance times the cosine of this angle. And then it shoots down to there. So that's the real moment. You could see it spinning clockwise from this perspective. So the other one has to spin it counterclockwise. So, it's not a huge time saver, but certainly the use of the program is visually, I think, instructive, and also helps to see, okay, well, this moment is spinning it this way, so the P3 would have to go down. We could probably animate that. This is spinning it that way. And then you could also see, well, it ain't spinning it at all if it's concurrent with the axis or parallel to the axis. So lots of nice little lessons. I hope you enjoyed it. Thank you.